Sí, bueno. ¿Qué tal? ¿Cómo están? Buenos días a todos. No, buenas tardes ya, ¿no? Buenas tardes. ¿Le pueden bajar la música? Gracias, qué amables. Bueno, pues como parte del Instituto de Materiales Avanzados para el Motor Sostenible, hemos venido organizando una serie de seminarios y conferencias, y el día de hoy me da mucho gusto presentar al doctor Gabriel Luna Bárcenas, como investigador invitado a que nos dé una plática sobre, pues el tema era Smart Materials, ¿no? Smart Materials. El doctor Gabriel Luna es investigador titular del Cinvestav Querétaro, tiene su doctorado en ciencias de la Universidad de Texas y un postdoctorado en Princeton University. Es investigador nacional nivel 3 del SNI y tiene diferentes líneas de investigación. Particularmente, él ha venido colaborando con nosotros los últimos 6 meses en el instituto, ayudándonos a definir pues un área muy importante de investigación, que es el área de biomateriales, con diferentes aplicaciones al área médica, al área industrial, pero sobre todo la parte de biosensores. Nos da mucho gusto que Gabriel, pues ya lo conocemos, tenemos varios años de conocernos, sobre todo que ha sido también presidente de la Red Nacional de Nanotecnología y también es socio fundador de la red Nanotox, que es el Sistema Nacional de Toxicología y Nanomateriales. Entonces, nos da mucho gusto que estés con nosotros, Gabriel, y bueno, pues te paso el micrófono, creo que traes un micrófono de solapa, y bueno, tú siéntete en tu casa y bienvenido nuevamente. Damos un aplauso, por favor, gracias.
Gracias. Buenas tardes, muchas gracias por la invitación. ¿Es en inglés, verdad? No.
Sí.
Thank you very much for the kind invitation, Arturo, and I want to extend that to all the people around here, and I know you're busy. And well, without more words, I like to start by saying something about myself. As Arturo mentioned, this institute that was just established here at Tec de Monterrey is not only a good thing for you guys here, but also for the Mexican scientific community. Because, as I said, not only will address some of the challenges in terms of manufacturing, CO2 emission reduction, but as well some of the vision that we also share as a Mexican society. We want a better Mexico, we want better jobs, higher paid jobs, and I think this approach of establishing this kind of vision from a private institution is a landmark for Mexico. So congratulations, and it's really a pleasure being here. To get started, let me start by just for you to get a feel of what the trends of the, according to the World Economic Forum, what the materials for the future, for a sustainable future should be. And of course, that could be part of a debate, but in principle, if you look at this chart, sustainable polymers, materials for the future, artificial intelligence are not only the future, but right now it's happening. And I'm sure that we all recognize artificial intelligence in the iPhones, cell phones that we use for everyday activities. And you may wonder that the mission of the Apollo, I forgot the number, that put the first man on the land, had a computer power of no less than nothing compared to an iPhone or a Samsung, just to be correct for other brands, I'm sorry. And well, there are other interests in according to IUPAC, the International Union of Pure and Applied Chemistry. And I wanted to mention that to you this afternoon because there are some challenges in terms of the emerging technologies and innovation. And I think the Institute of Advanced Materials and for Advanced Manufacturing is right on the money in terms of some of the challenges, especially recycling better materials, less polluting materials, light materials. So the economy could be a circular economy in this concept that we are all interested. So I'm not going to go in detail, just for you to give you a feel. And just to indulge your eye, let me show you a series of photographs that will try to convince you that nanotechnology, which is the topic of my talk today, is an important endeavor, not only from the scientific point of view, but from technology. And wonderful things happen in the transistor, the proper wetting phenomena to self-heal materials, from microelectronics to flexible electronics. I'm sure you've seen this mobile that you can fold it and nothing happens, and you have a bigger screen. And all of that is because of nanotechnology. The question is, are we ready to tackle those kind of applications in a country with all the challenges we face in Mexico? Obviously, the answer is yes. How to address that? Well, that's the challenge. And that, I think that's part of the institute. Well, can you continue? Okay, if you follow the red arrows, I'm sure you've seen that before, but the idea is that up to this central left-hand side micrograph is about the resolution of the most powerful microscope on Earth. More or less, the Japanese claim that they can go to a few nanometers. European companies, they claim to 1 nanometer, but no matter what they say, that's about the limit. And the limit is not imposed of technology, it's imposed because of a very basic scientific principle. It's the Heisenberg principle that we cannot pinpoint an electron position in space at the same time. And then the nature of these interactions become fuzzy, and that goes to the quantum side of the matter, which is an esoteric territory, because there are wonderful things that speculating may happen. If you remember the winners of the Nobel Prize just recently, they won it, and let me coin this phrase, because reality can be constructed. That's basically the moral behind the Nobel Prize in Physics. And at that level of manipulation of matter, we can experience wonderful things. Do we have the power to manipulate the energy at that level? No, not yet. So basically, that's my excuse to use microscopic techniques to address some of the quantum mechanic world, with the hoping that we can manipulate at that level the matter to have functional materials, better materials. The last picture, the last two pictures are just a cartoon. What we think they should look like, because matter at that level, unless we change the physics of what the Heisenberg principle, uncertainty principle tell us, it will be impossible to know how they look like, because the perception of matter, volume, space becomes fuzzy. We don't have the knowledge. I just wanted to address that. In this scale, you could see the breadth of different structures according to the size. And for instance, and I tend to criticize myself and my colleagues in nanotechnology. I don't know if you've seen some conferences on nanotechnology, and I think it's overwhelming, the number of publications in which they show micrographs, high-resolution microscopy results, showing some nanometric features. Just to remind the audience, 1 nanometer is a thousand of a micron. So it's 1,000-fold lower than a micron. So that's the kind of dimensions we're talking about. And if you have if you want to claim yourself as a nanotechnologist or nanoscientific guy, it's important to know that the ISO regulation tells that 100 nanometers or less, you have a nano object. Fine. That's a very obscure definition, but that's what we have right now. But the reason for that is that it's so diverse the kind of materials, is so diverse not only the structure, size, but functionality, then to address the proper definition of a nano object is not yet resolved. For instance, as I said, the ISO regulation tells us that 100 nanometer or lower is nano. Thank you. However, my perception, and I like to make it compelling to you, that is not sufficient. And the reason I say that is because, as I said, divide 100 nanometers by 1,000, and then you have 0.1 micron. So even from the semantic viewpoint, 100 nanometer or 0.1 micron is micron or is nano. Okay, but that's what the ISO is. Por favor. I'll leave that question for, and I'll address that in a minute. Okay, well, what the technology has done for me today? Well, the transistor, iPhones, iPads, whatever you think about that. And there is a responsibility behind that, because what is the fate of a nano object? Imagine you comminute some ceramic, some pollutant, down to nanometer scale size. Where's the fate of that? Will that go to my drinking water, to the river? Of course, that's a challenge. So we have to be responsible in what we claim we can do in terms of a sustainable future. And I think that's what the Institute is all about. In this graph, you could see the trend, and most materials are based upon silver, carbon, titanium, gold, just to give you a feel. I'll leave that roll, please, continue. No more explanation in terms of what right now, today, applications are up to. Let me switch gears a little bit from nanotechnology and some common applications so far to the biomaterial market. And the reason for that is because we're interested in the health and the environment applications. And that's a nice piece of business that we have there. Of course, we have to be smart, we have to be aggressive, and sometimes it's very challenging. I'll say most of the time it's challenge world in terms to not only produce a functional material, but to have the blockchain technology and the proper delivery systems and marketing, and that sometimes kills some projects. So I think it's important to understand that. And in terms of smart biomaterials for health, you can find cosmetics and stents and cartilage repair. And just to give you a feel of what the nanotechnology can do for us today, if you have an ear, artificial ear, made out of high-density polyethylene, which is an analog of low-density polyethylene plastic bags when you go to supermarket, with the proper technology, you make it high-density polyethylene, and the high added value is 1,000-fold minimum in terms of the revenue that you could expect. How to do that? Precision chemistry, who holds this kind of materials, big companies outside Mexico, even though we have the raw material. So I'm not going to get political about that, but just to our young listeners, that's a challenge that we could try to tackle with the proper education, with the proper resources, and I think I'm just rephrasing what other countries have done, especially in Asia, right? So okay. Don't get too scared. I'm just going to go light on this slide, but it's important, at least from my point of view, to tell you a short story about the science behind nanotechnology. Please hold the information I said so far, and we'll return after this slide. If we look at the upper left-hand side, we have a graph in where the y-axis, we have the electric conductivity. Imagine you have a Imagine you have a matte piece of paper, a piece of material, laminar, film, whatever you want to think about that, which is not conductive. Imagine I put 2 electrodes and apply a discharge of electricity. It does not conduct, especially this plastic, right? That's no-brainer. I start adding some nanospheres, little spheres of a metal, gold, silver, copper, any metal you think of initially, and then you start adding randomly. And once you have a random walk that connects touching 2 nanoparticles, and then you are able to construct from the point on where you have the one electrode and the other electrode, and then we have a conducting path, then the material will conduct electricity even though the matrix does not conduct it, right? That's very simple. Well, in that graph, you see a very low conductive material, and then it starts to take off as soon as you start adding more metals or anything that conducts, carbon nanotubes, graphene oxide, and other exotic current materials, until you have a saturation. Fine. What about that? That's a known phenomena for many years. Well, if you see this sigmoidal shape behavior, think of the middle point, and that's exactly where the conductivity starts to take off, few orders of magnitude higher compared to the initial non-conductive material as this cover of my phone. And then in that regard, this concentration in which that taking off conductivity happens, it is called the percolation threshold, from the Greek percolare, which goes through, basically. I can percolate through an audience, excuse me. So that's basically the same thing. And then that percolation threshold is a classical physics phenomena. The deceiving part is that the concentration required in a classical 2-dimensional, 3-dimensional system tells us that we will need more than 66% of the discrete phase of the conductive phase. And when you go to the literature, and we experience that, and I think that's part of the reason I got into this kind of research, is that percolation threshold happens 1 order of magnitude lower than the classical theory expects. And then you face a problem. You're seeing quantum effects, but we don't have the tools or the knowledge to understand the manipulation of matter, but we're able to see that that system percolates at 1 or 2% compared to the 65%. So can I apply the theory of the classical physics to these kind of concepts? We believe so, by manipulating and coming up with an idea. If you look at the central upper picture, that's the idea of the white part is the non-conductive matrix. And then the black spheres are the conductive in a 2-dimensional material. Well, one way to use classical tools for these non-classical phenomena, and we came up with this very simple idea, is to think that we have an effective higher volume as compared to the actual volume that you image by microscopy. That means that we have an interfacial shell with a pseudo composition between the matrix and the sphere. Of course, in this cartoon, we have hardcore objects. Materials, matter are not hardcore objects. We have ions, we have electrons jumping and for different orbitals, or ions going through different materials, especially if you have the path to go through. So in that respect, that effective bigger shell allows to have an imaginary contact without actually having the contact. And we have taken that theory further. And we have proved it and probed it by different kind of composites. think now, look at this graph. We have those are actually experimental data from our laboratories published in that paper, in the journal. The conductivity is a function of the composition of carbon nanotubes, which are conductive. If we have a matrix that has the proper molecular interactions, such as chelation, cation exchange, or any other different mechanism, look at the blue dots, it's a functionalized material. Many people do acid, basic treatment, laser ablation, radiation to erode the nanotubes and expose double bonds instead of just single bonds, carboxylate, hydroxylate, or induce some defects. If you have the proper polymer matrix, the material becomes non-conductive, even though you have used carbon nanotubes, which is a highly conductive electrical material. And this could be deceiving, but we have proved that before. So for instance, if you don't have the proper polymer matrix, look at the red line, we see the classical expected conductivity phenomena just described before. And well, the dotted line is what you would expect if you use classical percolation threshold. But if you kind of see the concentration in which this percolation threshold happens is between 1 to 3%. And then you wonder why it's not percolating up to 66%. But the reason is, as I said, these quantum effects. And one way to address that is to think about larger particles, even though they are actually smaller because of the interactions. If we're not there, how do you construct this interfacial shell? By allowing different interactions of the nanoparticles of the discrete phase with the material. That's critical. So the proper design tells us you want a conductive material, you want a semi-conducting material, and these concepts seem very preliminary, but in principle, by manipulating this kind of not conductive, conductive, we may have a different variety of different materials with fine-tuned more properties. Is that useful? Of course it is. Well, percolation also happens when I perturb matter with mechanical energy. In the end, think of matter-energy interaction. I can perturb matter by electricity, magnetic field, heat, mechanical perturbation, ultrasound, UV radiation, X-ray radiation. In the end, is energy-matter interaction. How to probe the response of a material given different energy, well, that's what we all do in terms of understanding matter. One of the applications, and I'm going to take off, so don't get desperate. One of the applications are very simple, and I tend to be very cynical of our own work because the literature is plagued with thousands of papers that deal with the preparation of nanoparticles using green media, highly reducing agents to produce nanoparticles from different sources, and it's fine. But we believe in our group that fundamental knowledge is very important to design proper functionality of materials. That's fine if you want to do the other way around. Perform an experimental design, which is fine, it's mathematics, I have no complaints about that, and spend a lot of time and resources and try to make 1,000 exaggerating experimental design, or go the other way around, which I think is one way to do it. Probably industry doesn't have the luxury of what I'm saying, but I'm glad I'm on this side, and that's what we're trying to do. Next. Well, we synthesize gold, nanoparticles, from a precursor, hydrochloric or chloric acid. Very simple. 500 papers on that. The difference is that we use this information, these concepts that I explained to you, based upon percolation that are in these papers to design the proper material. To our surprise, we were able to bring down the concentration of silver nanoparticles, copper nanoparticles, cadmium nanoparticles, barium titanate for flexible electronics. We have published that. Let me do some advertising of our group. We have addressed different materials with concentrations down to 0.5, 1%, so it becomes very inexpensive. And the methods that we use are very simple to perform in any basic chemistry laboratory. And in that respect, we did this testing of a patch for burns of second degree in a rat, following all the protocols and all the requirements to carry out this properly. And well, next one, please. On the right-hand side, you see the healing. And to our surprise, and to our colleagues, doctors, physicians, we have developed a non-callous cicatrization process, which is one of the challenges when we have a cut in our hand or any lesion, is the marks that are left, especially when we're interested in not showing some scarf on the face or whatever, right? So next one, please. I'm gonna go fast. Another application is to use the metabolic machinery of different bacteria to self-assemble nanoparticles, not by artificial chemistry, top-bottom approach. Now this is bottom-top approach, which is fine either way. And in terms of that, we were able to synthesize silver nanoparticles. Next one, please. Next one. Just to give you a feel of what the nanoparticles look like, not really surprising. That's 1,000 papers that relate to the production of silver nanoparticles, to be honest with you. So I'm not going to come up all the way to Monterey to tell you what you already know. Next one, please. But, next one. That's the initial approach. We have hypothesized, according to other researchers worldwide, that it's important to pinpoint which strands of bacteria are really helping the self-assembly of the nanoparticles to induce a reduction process. Otherwise, you end up with, just add silver nitrate to some effluent water, wastewater, and see what happens. Yeah, you could do that. So this is just to give you a feel of some industry that is based in Querétaro. This is the wastewater. I cannot say more than that. Next one, please. Just to give you a feel of that. We have extended that to pinpoint exactly the kind of strands. Next, sigue. And that's that picture on the right-hand side top. That's a different concentration of silver nanoparticles, just to give you a feel. Of course, that graph actually that supports the picture is telling us the kind of concentration that we produce, starting from silver nitrate, precursor material. Very simple, very simple. You can do it in your lab. You disperse silver nitrate, add the proper bacteria with the proper identification of the RNA or microRNA or the strands of that particular bacteria, and we get different, pretty good correlation of concentration of silver nanoparticles. Next one, please. Mass. That's to give you a feel of silver nanoparticles. No más? Okay. I'm returning to percolation. What we discover, and we have tried to compel to the scientific audience, and is paying off nice rewards in terms of citations, but citations are important, but I think it's important to try to make something that you could sell to pay our salaries, right? Well, look at the two graphs on the left-hand side. You see the percolation threshold, more or less around 2.5. We have a special software. You can construct two tangent lines and There are different methodologies to find the geometric approximation of where the percolation threshold is on the upper hand side. On the lower hand side, look at the behavior is slightly different, but actually we can bring the percolation 1% lower. How to achieve that? We manipulate the reaction very simple, recognizing that silver is a metal, and we're using the metabolic machinery of this bacteria, which is not a very aggressive reducing agent, that initially we thought it was a drawback, but in the end it turned out to be a good thing. And basically what we're trying to achieve is that different synthesis methods are producing different kind of particles. You see that number on the two graphs on the right-hand side. That's XPS spectra. No need to explain in detail. Just look at the numbers. Those percentages are the ionic silver. If you use a strong reducing agent, you end up with 99% of metallic silver. In other words, that number will be 0.11 instead of around 18. That number reflects the amount of ionic silver, silver plus 1. So what we discover is not only percolation help us to design proper materials, but different synthesis methods are producing different particles. And we faced this in the hard way. For probably over a year, we were not able to understand buying commercially available from Sigma Aldrich silver nanoparticles with very low reproducibility. And then we end up studying why that's happening. And part of the reason is that commercial nanoparticles are being synthesized with a strong reducing agent. And the percentage of ionic silver is minimal as compared to our more environmentally friendly methods of synthesis. So, sigue. Una más. Más. By understanding the proper manipulation of percolation concentration, and from that knowledge, build up knowledge to understand that the presence of ionic silver versus just pure metallic silver makes a big difference, and we're trying to combine in a library of proper applications because the literature is so deceiving, even in high-impact journals. They completely overlook this kind of phenomena. What I'm trying to say, if you have not only the proper concentration, but the electronic structure, but also the balance between ionic and metallic silver, you will lose that battle. On the upper left-hand side, we have the colony-forming units of bacteria that are pathogenic, gram-positive, gram-negative. Look to the power of killing or bacteriostatic or bactericide effect of the nanoparticles designed this way. The usual trend is an exponential decay, and here we have a minimum. In other words, there is a maximum potency in terms of bactericide effect as compared to what the literature has told us for 100 years. Use more silver, colloidal silver, to use for your eyes, for your nose, and there are many stores that sells colloidal silver. But this minimum, in other words, maximum of potency, coincides independently from where the system percolates. So something is happening there at the atomic, subatomic world. So the moral here is that proper design of functional materials make a big difference. ¿La que sigue? This is confocal microscopy of proper design of materials with silver nanoparticles. Just to give you a feel of the things that we do, we have extended this treatment to address other aspects. These recent publications, we have used a thermophile bacteria. It's called Deinococcus radiodurans. We were able, in collaboration with my colleague Lydia Contreras in Austin, Texas, UT Austin, we were able to isolate the correct strands that are doing the reducing effect on the silver nanoparticles to use for photodegradation of 6-N-rhodamine and all that. We have, we have performed the development of an oxygen sensor. Very simple. There are 102.5 papers, you tell me what the 0.5 means, about to design zinc oxide nanoparticles for different applications. If you do percolation, think behind the rationale of designing materials, we were able to design a oxygen sensor. And look at the upper right-hand side. That's a circuit. You see this little part of paper? That's paper that we used to write. Well, every time we write less. Treat it with an acid, embed with zinc oxide particles. And then we have a UV LED. We shine the light through. And what we discover is that it's highly sensitive to the oxygen present. Honestly, this is not going to compete with a commercial oxygen sensor. That's too expensive for that application. But it's very sensitive. The lower the concentration of oxygen, the more sensitive. So this is especially for some special applications in which you require less oxygen, or it's critical for some microbiology assay, whatever. ¿Que sigue? We have also developed a glucose sensing device with this kind of mindset thinking. ¿Que sigue? Más? Very simple. We have a chitosan. Actually, I forgot to mention that in the previous application we use chitosan because we're the chitosan guys. And chitosan is a natural polymer, not naturally occurring. The precursor is called chitin, but the most abundant version, commercially available, is chitosan. And the beauty of that chemistry platform is that it's a linear glucoside polymer. Imagine spaghetti. So if you are familiar with the polymer world, it is hard to find a polymer with abundant primary amine groups and hydroxyl groups in the backbone chain. There, to my knowledge, probably another one, and that's about it. And that's a very interesting platform. So we use that as a proper interaction to promote proper interaction with the nanoparticles according to what I expressed before in percolation threshold and all that. One way of addressing this kind of challenge is by recognizing that nanoparticles in the nano world are not a magical world yet in terms of the design. If you bring polystyrene, polymethyl methacrylate, polyurethane that is used in medical applications, commercial applications, and you just think that adding a nano object will be sufficient to produce a functional materials, wrong. And, ¿qué sigue? ¿Más? Well, we chose, and Roberto Parra will criticize us the way we did, so simple. The pair enzyme substrate, we have glucose oxidase, and the substrate is glucose. So we have this voltagram representation of the sensing capabilities of our device. ¿Sigue? Una más. This table shows our benchmarks compared to what other researchers and some commercially available sensors are. We have pretty good sensitivity. It's the highest we found reported. To be strict with myself and to you, of course, we publish this in peer review, high impact journals, and we have the highest sensitivity. The linear range, well, it's not too bad, and of course we could do better, but I think we have the proper manipulation of matter to produce a sensor, nanosensor. La que sigue, por favor. This is, I'm so happy always I show this. The reason for this is that the pictures are not taken from the web. These are actually pictures of kids in Mexico City. There are actual patients from the National Rehab Institute in South Mexico, close to where you are. And Well, bad news is Mexico is second in cleft palate of newborn babies. That's how they account for that. If a boy or girl dies during birth with cleft palate, is not accounted for. It's just living people. We're number 2, not only diabetes and cancer, that I'll go in a minute into that. La que sigue, por favor. La que sigue. Una más. Más. Well, we have designed hydroxyapatite artificial comminuted to nanoparticles, use high energy milling, very simple, with a material based upon these polysaccharides, xanthan gum, which is used in the food industry, chitosan, as I expressed to you. Xanthan gum is a branch polymer, chitosan is a linear polymer. I'm skipping a lot of these details, but just to give you a feel into the young audience, we are combining the structure of different kind of materials to gain the proper balance between hydrophilic, hydrophobic, percolation, concentration. It's starting to become a rather complex pictures, but I think we have a pretty good idea, at least in terms of the application I'm showing. And you see the central graph, the flow cytometry, in which we have the CD 73, 90, and 166, which are related to the osteogenesis. So we are promoting with our material and the proper factors to induce the osteoblasts to go to osteocytes. So we do that in about 80% higher, but let me be more responsible. And this qualitative picture on the left lower side, una menos, the black part is where there's some calcification. So this is a qualitative picture, but we're having calcification. ¿A que sigue? Well, we have also worked with my colleague Luisa Rocha in Cinvestav Sede Sur. She is a wonderful woman in terms of the contribution to epilepsy. I think she's number 1 in Mexico in terms of epilepsy research and probably in Latin America according to the metrics, not according to me or my perception. And we have designed magnetic nanoparticles decorated with silicon-based tensoactives of amphiphiles to load phenytoin, which is the main drug to treat epilepsy. Let me tell you something. Mexico has about 500,000 epileptics. That's really high. And about 10% of that, they have something called refractive epilepsy, which means that phenytoin does not good at all, because if they take the phenytoin in a typical epileptic people, it will help them. But because there is some barriers, especially brain-blood barrier, barrera hematoencefálica, BBB, that is a bomb producing of electron chemicals that are overexpressed in people with epilepsy, and basically erases all the possibility of this phenytoin go through the BBB and reach the brain and do the good thing. That's a bad thing. Well, ahora sí el video, el primero. I'm going to play a short video in which we have induced with all the proper medical protocols. El que dice convulsiones, no sound, please. We have induced epileptic seizures, excuse my Spanish, epileptic seizures with 3-mercaptopropionic acid. It's a well-established methodology in the medical community in atymic rats, not mice, rats, to induce what we have in humans, an epileptic seizure. You see the poor animal. La que sigue, por favor. After the injection of the magical nanoparticle system loaded with phenytoin to deseed the BBB, that's basically what we're doing. If we have bulk dissolved in the bloodstream, the phenytoin, this BBB in these epileptic refractive people will not let it go through. It will not percolate, to be proper with the initial of my talk, right? So we kind of cheat the BBB by having this carrier. And if you induce 0.1 Tesla magnetic field on the head of the person, that's the idea, we can self-induce. That's also very known concept. Like, el otro video no me lo pasaron. Es el bueno, pues, si no, pues. Ya casi termino. Look at what happens after the injection of the nanoparticles. So difficult to assess the quantification of how much phenytoin was delivered to the brain with this kind of weight of a rat and the nano concentration of the phenytoin. How we do it? Well, we did some cuts in the frontal core of the brain that is well documented in the Listo, in a nanomedicine paper, which is based in London. We did that in Siglo XXI, IMSS, Mexico City, with many people involved. And we have strong evidence that we were able to cheat the BBB and deliver in this, with this nanocarrier, the phenytoin. Of course, let me tell you some of the challenging questions. You want to saturate your brain with a metal. Why don't you do this in a non-metal carrier? Well, we're working on that, but it's being very difficult. I think I'm going to skip that. La que sigue. There are some applications for sensor of cations and ions. Más, por favor. Ahí. Bueno, una más. I'm sorry, I had to skip that, but it's basically using percolation to produce some sensors for cation and ion sensing with very good capabilities. Not as good as we thought, so I'm skipping that part. We have patented this little toy I'm about to tell you, and then I will finish. Everybody should show a big smile because I'm about to finish, right? Thank you, Bere. She was the first one to smile. We have synthesized magnetic nickel nanowires. Another 100 papers to how to do that? Yep, of course. ¿Que sigue? We have done that in our laboratories. Dale más y ahorita te digo que te regreses, lo siento. Más. Más. Una más. Sorry for that. I know a friend who is a very good scientist and he goes 3 slides ahead and 4. It's like a random book and I'm becoming like him and I used to criticize him, sorry. Well, this is the little toy. On the left-hand side, you see a little box that we have constructed of PMMA, polymethyl methacrylate. And if you see, there is some coil of copper, a line in this position, and then perpendicular, right? In the far back. Then we have a laser, a red laser. And in the middle, there is a space for a cuvette that you use typically in a UVB spectroscopy measurement. Very, very standard. And then instead of, when we shine the laser, instead of looking at the transmission, we look at the reflection, at the dispersion at 90-degree angle. Well, sometimes it's good being naive about a project, right? It's a completely very different, exaggerating ball game. Transmission is a phenomenon that is kind of simple to understand, but dispersion, I'm glad I'm surrounded by physicists in my institute. Good thing they are good for something, right? They say about the same thing about me, so it's just a payoff joke. And then you see on the right-hand side, a top view from an iPhone, you see the laser going through. And then you see the square receptacle, which is a cuvette, 1 centimeter by 1 centimeter square section, very typical. Ahora sí, vete para atrás, por favor, más para atrás, más. Más. Una más. Ahora para adelante. Una menos, por favor. Ahí. Well, this is just a small animation in which we load a colloid of nickel nanowires, right? Magnetic. Then I apply a current which induces a magnetic field. And I turn the two parallel, okay? Then I'm going to switch that off and turn the anti-parallel to that. And then I keep doing that, but I have to fine-tune the frequency in which the nanowires will rotate. ¿Sigue? I apply the voltage, the magnetic field, una más. And then I have moving the nanowire. You may think that's an act of fate, but we have actually proven that. To give you a feel, between 5 and 10 hertz, that's the frequency, natural frequency of this kind of materials. Of course, because they are made at home, we have, every time we have a fresh batch of nanowires, we have to fine-tune. That's probably one of the drawbacks of this technology still. But it's very simple to do. Well, we did some simulations with COMSOL, trying to understand the moment of inertia in a viscous fluid as compared to vacuum, and then that brought some complexities. But I'll tell you the story about the physics later. Like, sigue? How does this work? If we have this rotating nanowire, which I have adjusted with the natural frequency, and we have the photons coming from the laser, what we're doing is just sending in dispersion. We have a photosensor on the top. If I change the moment of inertia, which means I change the mass, I pick different signal, and then that's an indirect way of detecting how much concentration of nanoparticles I have. I can attach in a smart way an oligonucleotide. That's what we're doing. I'm not going to discuss that because that's still proprietary. And then we can detect how much of the protein is coating or decorating, whatever the mechanism is, the nanowires indirectly. ¿La que sigue? Una más. Hay una animación embebida ahí. Si le pones, pone el ratón, ahí está, si le ponen. That's the electric field off. Then we're going to turn it on. You see the widening. If we're not able to rotate the nanowires, you see nothing. So that's an indirect proof. Very simple. So that is rotating. Then we turn it off in a minute. Well, in seconds, right? Minutes, we'll fall asleep. Listo, la que sigue. Más. Una más. Más. We have addressed some of the issues related to cancer at a very preliminary stage. I'm not going to claim we have done any extraordinary. We're working with this kind of thinking in producing self-nanomulsifying drug delivery systems, also called SNEDs. This term was tagged by a professor at UMass, McClements, highly cited researcher. And we just published this recently, and on the upper left-hand side, we see all the parts of the intestine, stomach, mouth that a rat was imposed to when we injected the dose of these SNEDs, which contains betulinic acid, which is known for the anti-cancer activity. And the idea is, once again, how can I pass through different chemical barriers, pH, electronic surrounding that is medicine is encountering as it goes through our body. And you have, and I have experienced the problems of that not understanding correctly. Why? Because they give us overdoses of antibiotics or medicines, because doctors know that probably 80% will go through liver or other filters that we have in the body. So the idea, basically, the rationale is how can I deceive all these barriers to minimize the dose and reach the target. So, ¿que sigue? Una más. Let me finish by thanking our sponsors because it's important. On the upper left-hand side is fading, but that's what it is. La que sigue, antes de que me cachen lo que dije. That's a recent picture of the group. Una más. And I want to really close my talk by expressing my highest gratitude to past members of the group. And right now, well, you saw the picture of the students from postdocs, but this is the list of people that have graduated from our group, and some postdocs, and very wonderful people, and highly talented, and it's a pleasure working with these kind of people. So thank you very much, and I'll be happy to take any questions if you may have. Thank you.
We have some time for some questions. Anyone? I have a question about the percolation threshold. How do you control that? How do you do it? You know, in different types of materials or different types of, and is that possible to really control the percolation threshold or not?
Thank you, Arturo. Let me rephrase if I understood your question. The system percolates no matter what when you have proper nanoparticles that conduct electricity or can dissipate some mechanical force. I explained electrical phenomena, but could be extended to other type of matter-energy interaction. And it's going to percolate no matter what if you embed, if you dissolve, if you just add that conductive or that material that has these wonderful properties into a matrix that is going to be responsible for having a patch, a film, and not just have the nanoparticles pristine. It's going to percolate no matter what. One way to control that is by looking at the chemistry of both materials. For instance, if we have silver, which is 99% metallic silver, silver zero, and you add it to a polymer, you will experience percolation probably even close to the classical percolation threshold. If you, in advance, produce by manipulating the reducing agent, not too strong, not too soft, or you can go too strong, too soft, and we have categorized that spectra, we will produce nanoparticles with ionic silver. We kind of understand that, and we have the way to do that. If we have, for these biomedical applications, 10, 20% of ionic silver with the proper matrix, we will experience that the concentration expected for percolation will go down 1 order of magnitude or less. For different objects, we have a master curve. It's like a calibration curve. Silver with no ionic content will percolate at higher concentration. With more ionic content will percolate lower concentration. Gold, everybody think that gold is an inert material. Well, wait a minute. When you come in to 10 nanometers, you have gold plus 3. And then gold becomes very reactive as compared to what we think is non-reactive in micron features. So basically, in advance, based upon this experience, we can design where the system can percolate. And if we look some functionality, we can tell in advance which synthesis method is best, so we can kind of predict where the percolation will be. But we reached this point based upon many experiments. Otherwise, it will
because the threshold will be the minimum connection that you require in order
correct.
to change the,
That is correct.
the physics of the metal.
That is right. And just to finish that argument, if you don't have the proper matrix, the presence of the interfacial shell is not there, and you need that to minimize the concentration and to have the functionality. The initial papers that we published were very difficult to get them across because, show me how big is the interfacial shell. Luckily, we have been able to have a feel of different materials, could be between 1 or 2 or 3 nanometers, which brings an extra dimension of the nanoparticles. That is working so far, but when we go to lower dimensions, to 1 nanometers, I think our theory breaks down because you start to see some quantum tunneling, and that's, well, I think that's we have to go also in that direction. Thank you, Arturo.
Thank you. Any other questions? Yeah.
Well, Gabriel, excellent presentation, very enlightening. Thank you. But I have several questions regarding the wound healing. This is a big market. I don't know how easy it is to get that product because I think there is a pathway to get it in the market. I don't know if you evict that because that's a nice product for the future.
Thank you, Roberto. You asked a bad question, but thank you. Good thing you're my friend. As you know, and you have experience on your own, to go from this point to the market, it will require some additional testing, preclinical test. You have to convince people. You have to invest some money in terms of getting the right testing. However, it's doable, right? It's probably just the lack of, to be honest with you, it's just the lack of training or the lack of correct mindset to get that across. But that's what the Institute is for, right? Yes. There you go. That's your answer.
Okay. Any other questions?
Thank you, Roberto.
Oh, yeah, Pedro.
Pedro. Thank you.
Thank you. I would like to know a little bit more about the nanowire. Do you have information about the magnetic field, the behavior of the magnetic field?
Not experimentally, but we're doing simulations. We hire a very brilliant physicist from Ukraine, to be politically correct these days. He's doing some simulations in which he actually has, right now he's doing with the sphere, because it's a more simplistic approach, and we can gain a lot of physics on that. And I forgot the name of the software he's using, but he's actually simulating different strengths of magnetic fields and try to understand how that thing moves or if there's an interaction. This is not a joke what I'm going to say, but when I get back to back home, to my place, we'll have a discussion on how things are going in that simulation. So right now I have no more information than telling you that we are addressing that issue. It's very important to understand what the magnetic field is really doing. And,
because it's like a nanowire, so the performance of the magnetic field is connected with the wire.
That is correct. That is correct. Let me tell you a self-cynical comment. It's easier to explain what works as the opposite. So right now it works. If you give some time, I'll tell you what the physics is.
Thank you very
but
much.
Right now, I have no more information. But we're working on that, really. Honestly, we're working on that.
Thank you very much.
Thank you, Pedro.
Well, is there no more questions? No? Okay. Well, thank you, Gabriel, for your excellent
Thank you.
presentation, and thank you.
Thank you all.
And thank you all for your participation. Thank you. Thank you to the people who was connected online also. Thank you. Bye. Muchas gracias.